Bonjour tout le monde. Hello everyone. So we're here for the lecture of the André Aisenstadt Prize. This prize was launched by the CRN in 1991, aiming to recognize exceptional achievement in research by a young researcher less than 8 years after their PhD. And this year, the prize winner is Alexander Kupers, and he obtained his PhD in 2016 at Stanford under the supervision of Soren Calatsius. And after a postdoctoral position in Copenhagen and another one at Harvard, he joined the University of Toronto in 2020. And he was awarded the André Aisenstadt Prize for exceptional work on problems related to the classification of smooth manifolds. And he will talk today about the diffeomorphisms of disks. So please go ahead.
OK. Merci pour l'invitation. Je suis heureux de pouvoir vous parler de ce sujet aujourd'hui. Malheureusement, je devrais de faire en anglais. So I took 5 years in French in high school. I feel a bit sad that I couldn't give the talk in French, but then I realized in high school we spent twice as much time learning Latin, and I can also not give this talk in Latin. So English will have to do. So I'm going to tell you about diffeomorphism groups of disks. I'll actually spend most of my time just talking about work from, I don't know, 50 to 20 years ago, explaining what was known, and then I'm going to tell you about recent progress that we've made. And if time permits, tell you a little bit about why this progress was possible only recently. OK, so what is a disk? Here's a picture of a two-dimensional disk. It's just a subset of d-dimensional Euclidean space given by all points that have distance at most 1 to the origin. This is an example of a d-dimensional smooth manifold with a boundary given by a d-1 dimensional sphere. And in the precise sense, it's the building block of all d-dimensional manifolds. This is the theory of Handel decompositions, or Morse theory. By gluing these guys together along parts of their boundary, you can build any manifold. So I like to say that in some sense it's the most important manifold to understand. And I'll try to make it more precise momentarily. So if you think about the category of smooth manifolds, and this as an object in it, you should probably also care about what the symmetries, what the automorphisms are of this object in this category. And those are the diffeomorphisms. So these are the smooth bijections that have a smooth inverse. I'm going to demand that they restrict to the identity on the boundary. Does this really matter? Not really. Any diffeomorphism has to send the boundary to the boundary. Inductively, if you can understand the diffeomorphisms of d-1 dimensional manifolds, you can understand what the difference is between restricting to the boundary, the diffeomorphism being identity on the boundary or not. And it turns out that this is slightly more convenient for a bunch of arguments. We'll see that in a second. It allows us to do certain gluing constructions. Yes?
When you say it's so smooth on the closed disk, is that the same thing as saying that it's smooth on the open disk and all partial derivatives extend continuously to the boundary?
Yes. It's also equivalent to being the restriction of a smooth map on an open subset.
Oh, wonderful.
Yeah. I think that was proven by Hirsch. OK. So here's a picture of one of them. This one has some extra symmetries because that's the best I can do in TXZ. But they can do quite complicated things. So we would like to understand how many of these diffeomorphisms there are. And I can give you immediately an answer to that question. There's infinitely many of them, except in dimension 0. For the following reason. You can just take your piece of paper, keep the boundary fixed, maybe imagine it's made out of not paper, but some flexible fabric, and then start deforming it a little bit. Then you get some diffeomorphism from the disk to itself, and you can create infinitely many this way. But in some sense, many of those maybe are equivalent to each other in a sense. In the following sense, they can be deformed into each other through diffeomorphisms. So if you want to answer this question and not get an answer that always is infinity, you should count diffeomorphisms up to deformation. And what it precisely means is that you want to put a topology on disk. You want to give the topology where two diffeomorphisms are close to each other, if they have values that are close to each other, if they have derivatives that are close to each other, if they have second derivatives that are close to each other. Maybe this is some kind of Frechet manifold. Okay. The topology has the following advantage. It makes it a group in the composition. So taking an inverse and composing will be continuous. And the second advantage is that the path components admit a very nice description, namely of isotopic classes of diffeomorphisms, where you say that two diffeomorphisms are isotopic to each other if there's a one-parameter family of diffeomorphisms interpolating between them that depends smoothly on the parameter. So then the question becomes, from the point of view of topology, what is the homotopy type of this topological space? Okay, so homotopy theory is the study of topological spaces up to homotopy. But concretely, what this means is you want to compute invariants from algebraic topology of the following form. Maybe you want to compute the path components. We already said that those were isotopic classes, but how many isotopic classes are there? You want to compute the fundamental group of this space. Okay, you have to pick a base point for that. I left that out. Probably it's going to be the identity. So these are loops starting at the identity and ending at the identity up to homotopy. And there's higher versions of these homotopy groups where you don't map a circle in, but you map a two-sphere or a three-sphere in. These are the higher homotopy groups. So these are I-parameter families of diffeomorphisms. Now, you could also compute other invariants from algebraic topology, cohomology, homology, maybe not directly of this space, but of a very closely related space I'm going to tell you about in a second. Okay, so I said before that understanding diffeomorphisms of disks was an important thing if you cared about studying manifolds. I somehow tried to intuitively say this was important because all manifolds are built from disks. I'm not going to make this more precise. Like, why is this the most important case to understand, in my opinion? So, okay, firstly, there's some kind of tautological answer. By the description of the homotopy groups as I-parameter families of diffeomorphisms of disks, if you understand the homotopy type of this space, you understand exactly how many such families there are that can't be deformed into each other. Okay, it seems like a reasonable thing to do, but maybe not directly motivating. The second reason is that it helps you classify particular geometric objects. If you already know how to classify manifolds, the next thing you want to do is classify families of manifolds. If you have families of disks, those would be called disk bundles. I'll explain how to do that if you know this homotopy type. There will be immediate consequences for other manifolds. You can use diffeomorphisms of this to construct interesting geometric objects in other fields that are not differential topology. Say you're a symplectic topologist, say you are a Riemannian geometer. And finally, I think this is actually one of the most crucial ones. If you don't care about smooth manifolds, you only care about topological manifolds, maybe you're a person like that, it turns out that essentially the only way you can really access these is by studying diffeomorphisms of disks. And I'll explain how that goes, and this crucially appears in a bunch of the proofs that we might be able to say a little bit about. Okay, so let me start by explaining something about what disk bundles are and how understanding this homotopy type allows you to classify disk bundles. Okay, so here's the definition, but maybe let me try and draw a picture of it first. So what is the idea? The idea is that you have some base, B. Over that, you have some manifold. And whenever I take a fiber, the fiber should be diffeomorphic to a disk. Okay, how do you make that precise? You have this map, I call it P in the slides. The map P between smooth manifold, which is a smooth submersion. The fiber-wise boundary should be just a product of the base with a sphere of dimension d minus 1. That's related to my condition that I wanted to fix the boundary point-wise when I was looking at diffeomorphisms. But here's the most important property. The fibers should be diffeomorphic to a disk relative to the boundary. So the way to think of this is as a B-indexed family of manifolds that are abstractly diffeomorphic to a disk. Okay, this is a definition when the base is a manifold. There's a more general definition when the base is not. If you know what the definition is of a fiber bundle, then you know what this is. Okay, so the crucial thing that allows you to apply homotopy theory is that there is a particular space called the classifying space, which has the following two properties. The first one is that homotopy classes of maps into this space are in projection with disk bundles over your space up to isomorphism. Okay, this is some not so easy to understand topological space, infinite dimensional, very large, built by some general theorem about the representability of certain functors, but it gives you one space. If you understand its homotopy type, you understand exactly what disk bundles exist over any space, as long as you can do enough like homotopy theory, which hopefully you can. Okay, there's one thing that you do know about this space, which follows from its construction. The homotopy groups of this space, so mapping in a sphere and looking at all the maps from a sphere into this B-diff space up to homotopy, is the same as homotopy groups of the actual topological group, but the degree is shifted by 1. This follows from the construction, or one construction of this, which is that you can take a contractible space with a sufficiently nice action of the diffeomorphism group and then take the quotient. It should implicitly be free. Okay, so these are the only things that I'll use about this general construction that you can do. Okay, so let me do an example now, combining these two facts with each other. And that example says that the homotopy groups of this topological group of diffeomorphisms are the same as d-disk bundles over spheres. And how does that go? Well, we have a homotopy group of this space by the second property. That's the same as a homotopy group of the classifying space, but shifted by 1. Those were the same by definition as maps from a sphere into this space up to homotopy. They really have to be based, but in this case I can ignore that because this space has some nice properties. And then by the property of the classifying space, these are the same as disk bundles over a sphere up to isomorphism. Okay, so this is a geometric interpretation for the homotopy groups of this topological group of diffeomorphisms. You can make it even more concrete in the case that I is 0. So then the theorem, what I just said, says the following: the path components of this group are the same as disk bundles over the circle up to isomorphism. What are the two maps? They're very explicit. On the one hand, you can start with, if you have a, let's take an interval, but bring its ends close together. Now take a product bundle over it. Just take the product with a disk and use your one diffeomorphism to glue these ends together. You get something that's called a mapping torus, which now lives over the interval with its endpoints glued together, which is a circle. And so one construction takes a diffeomorphism to this mapping torus, a one-parameter family of disks living over the circle. To get back the diffeomorphism, you start with a bundle like this. Maybe I should draw a different picture for that. You start with a bundle over the circle. You pick an identification of one of the fibers with a disk, maybe this guy over here. Then you pick a vector field that projects to dd theta downstairs, and you flow along it. When you flow along it, you get a diffeomorphism when you eventually return from the disk to itself. That's the monodromy. This is the diffeomorphism from the disk to itself. That's only well defined up to isotopy because you made some choice of vector field. If you pick a different one, you can interpolate them to each other linearly. And when you do that, you get an isotopy between these two diffeomorphisms. So concretely, this tells you how this projection goes between path components of the diffeomorphism group and disk bundles over the circle. Okay. So that's one interpretation for one of these topological invariants of this topological group. The homotopy groups are the same as disk bundles. Okay. Let me now explain why, if you know something about diffeomorphisms of a disk, why that's very helpful even if you don't care about disks. So first is a construction that allows you to produce diffeomorphisms of all the manifolds. So what do we do in this case? We start with a manifold M. We pick some embedded disk inside of it. Okay. Now, if we have a diffeomorphism of a disk that fixes the boundary pointwise, what we can do is we can insert it here and extend to the rest of M by the identity. Okay. If I do that, I get a homomorphism that goes from the group of diffeomorphisms of a disk or boundary to the diffeomorphisms of M. So whenever you have interesting families of diffeomorphisms of a disk, you can also get them on a manifold. And it turns out, and this should not be obvious, that in many cases, the interesting ones for a disk survive in any manifold. We'll later see that maybe that there you can actually figure out what the difference between them is, and this will be used in some of the proofs. Okay, why am I talking about that? It's because it allows you to apply the following procedure, not just to disks, but to any manifold. What's the procedure? Suppose you care about special metrics, positive scalar curvature metrics or something on a manifold, or you care about symplectic context structures on either a disk or on a manifold M. If you have a diffeomorphism or a family of diffeomorphisms of a disk or that manifold, you can let them act on that geometric object. And you get some family of geometric objects or some geometric object that might be interesting if your family of diffeomorphisms was interesting. And here's an extreme example of this. If you take the symplectic structures on R4 that agree with the standard one outside of a compact set, then you can act on those by diffeomorphisms of a disk by inserting the disk just in the center of your R4. If you pull back the standard symplectic structure along diffeomorphisms, you get a map from the diffeomorphisms of a 4 disk to the symplectic structures with compact support on R4, and Gromov proved that that's an equivalence, a homotopy equivalence. So basically studying diffeomorphisms of the 4 disk is the same as studying symplectic structures. And in fact, you might imagine that this is the way you're going to prove something about diffeomorphisms of 4 disks, where we don't really have as many techniques as in low or high dimensions.
Is this special for dimension 4?
Yes. It's very special. Okay, finally, let me talk about these homeomorphisms. Okay, it uses the following very interesting idea, which is that you can define a space of smooth structures on a topological manifold M. One of the properties that it has is that if you fix a smooth structure, you can act on that by a homeomorphism. Oh, how does that work? Well, a smooth structure is some kind of maximal atlas of charts, and you can just precompose them by the homeomorphism to get another maximal atlas of charts. Some things will fix that maximal atlas, namely the diffeomorphisms. That's the definition of a diffeomorphism. So you get a map like this that takes the homeomorphisms quotiented by the diffeomorphisms and produces a smooth structure from the one you start with. The very shocking result, well, half of it is shocking. This is an equivalence onto some path components. So it should say multiple path components. If M is compact, that's the Ayres-Mann vibration theorem. Or if the dimension is not equal to 4, then it's Kirby-Siebmann, and it's very hard. Okay, so here's one example. When the dimension is not equal to 4, the smooth structures on RD are the same as the quotient of the homeomorphisms of RD. So those are just denoted by top D. That's just a notation for that. By the diffeomorphisms of RD, but those can always be deformed to linear ones. By like zooming in on the origin, you can approximate continuously every diffeomorphism of R4 by a linear map. And then I guess you can Gram-Schmidt orthonormalize it. Okay, so that gives you maybe some kind of description of the smooth structures on RD in terms of homeomorphisms and linear maps we understand pretty well.
Sorry, you said that for the diffeomorphisms of RD, you could just like pretend it's the OD.
Yeah.
Is that not true for disks?
No, because no, it doesn't, because this somehow involves pushing all your difficulties off to infinity where it disappears. But here, because we're fixing the boundary pointwise, you cannot do that. And even if you were just preserving the boundary setwise, there's no guarantee that you. So this would work if you looked at only those diffeomorphisms that preserve the radial coordinate in that case. But in general, they don't need to. I mean, we'll see in a moment that these groups are very non-trivial in high dimensions. And so this cannot really be true.
But you're saying that this OD is homotopy equivalent to
Diff of RD. That's true, yes. Yeah, it's a general thing that like on non-compact manifolds, things are often easier because you can push your difficulties out to infinity. It's easier somehow the smaller the core of your manifold is, and here the core is a single point. So it in some sense says that these diffeomorphisms are determined by what happens on a single point. Okay, so suppose now you have a smooth structure on a D disk. You can record what the smooth structure is near every point. If you look at only those smooth structures on the disk that are standard near the boundary, you will just see the standard smooth structure on RD when you're near the boundary. So this will give you a map from the disk to the smooth structures on RD that take value the base point near the boundary. And a very hard theorem from the 70s is that when the dimension is not 4, this is a homotopy equivalence. You should interpret this maybe as follows. It's a bit like you get local data of smooth structures near every point, and the theorem says that you can integrate that to an actual smooth structure. Okay, so combining this result with this map that I wrote down over here from homeomorphisms quotient by diffeomorphisms, in the case that M is a disk, we get the right equivalence over here. It turns out that the left map is also an equivalence. This follows from what I said before, that one construction of this classifying space is that you take a contractible space with a nice free action of your group and you take the quotient. So the claim is that, okay, diffeomorphisms acting on homeomorphisms is definitely a nice free action. The claim is really that it's contractible. And this is this famous Alexander trick, which is the following. If you start with a homeomorphism, that is the identity on the boundary, what I can do is I can deform it to the identity as follows. At time t is 1/2, I'll put the identity in this annulus of radius 1/2. And here I'll put my h, but now shrunken in size by a factor of 2. And then maybe at time 3/4, I'll have this picture. I'll be the identity on an even larger region. And then finally, when time t is 1, this entire disk will have shrunk to a point, and I'm just identity everywhere. What I've written down is actually a family of diffeomorphisms, except at time t is 1, at the origin, the derivatives will go to 0. And so it's not actually an isotopy. This doesn't work for diffeomorphisms for that reason, but it works for homeomorphisms, and those are contractible. So we have this equivalence, which is what Mollet originally proved. It says that you can understand diffeomorphisms of a disk in terms of homeomorphisms of Euclidean space. You see, what is the part of the right side that is the hardest? It's definitely the homeomorphisms of RD, this thing denoted top D over here. The orthogonal group is well understood by topologists. So the point is that the following things are essentially equivalent from the point of view of homotopy theory. Understanding the diffeomorphisms of a disk, the homeomorphisms of Euclidean space.
You're saying that the homeomorphisms of the disk is easy, and the diffeomorphisms of the Euclidean space is easy.
Yeah, sometimes you're trading them off against each other. But the point will be that even if you care about diffeomorphisms of a disk, having this other interpretation in terms of homeomorphisms can sometimes be useful. What's more common is that you understand the homeomorphisms of Euclidean space in terms of the diffeomorphisms of a disk. And you do that because for smooth things, there's just many more geometric techniques available than are available for topological things. Okay, so I guess that's the overview of these reasons we cared about this particular group. So what was known until about 10 years ago about these? It turns out that, as in general in differential topology, I guess, there's 3 different regimes. There's the low dimensions, where you can use particular geometric techniques. There's dimension 4, where there are techniques, and we can say some things, but I put question marks there because I think there's not really a completely satisfactory approach to this dimension. And then there's high dimensions, where things essentially reduce to algebraic topology. You have to be somewhat clever to do that, but that turns out to be the case. So let me first say what happens in these low dimensions. What do we know there? So if you have a 0-dimensional disk, that's a point. And the point has only one diffeomorphism, which is identity, so that's easy. In the 1-dimensional case, it's contractible. by the following picture. So let's see. So by the inverse function theorem, I could have said this before, having a diffeomorphism is the same as having a bijection, which has an invertible derivative everywhere. And in this case, that boils down to having a bijection, which is strictly increasing. Once you have to fix the endpoints, being strictly increasing effect is sufficient. And then you can just linearly interpolate and check that that preserves these conditions. You fix the endpoint still, and you still have a positive derivative. You're still strictly increasing. So that gives you a way of deforming any diffeomorphism of an interval back to the identity and tells you that that group is contractible. Okay, what about dimension 2? It's also contractible. This is a result of Smale, which in some sense is very similar. So I drew this picture over here, but maybe I can explain it a little bit. There's a bunch of other proofs too, but this is, I think, the nicest one. Okay, so the first thing is that you say, it doesn't really matter so much whether I talk about squares or disks. I can always insert a disk in a square and a square in a disk to relate the two to each other. And then whenever I have some diffeomorphism, I can get a vector field from that. What do? I just take the standard ddx vector field and I put it back along my diffeomorphism to get another vector field that maybe looks really strange, but because my diffeomorphism was the identity at the boundary, here it still looks standard. Okay, that's one thing that you can do. You can then try to recover that diffeomorphism as follows. You can start over here and flow for some amount of time along this vector field. And when you do that, you actually get the value of your diffeomorphism at the point y, x given by the time coordinate. So that's what Smale observed. And then there's something special in dimension 2, which is that this construction actually allows you to construct a diffeomorphism from any vector field that's everywhere non-zero and is standard, this ddx near the boundary. And then you just interpolate these vector fields to the standard vector fields. What is special here about dimension 2? In high dimensions, if you try to run this argument, you could get stuck on some kind of limiting cycle. But in dimension 2, that doesn't happen by Poincare-Bendixson. There's something special here. So this argument would not work in higher dimensions. Okay, but the point is that the vector fields that are everywhere non-vanishing and are ddx at the boundary, that's a contractible space. And so the diffeomorphism is also contractible. What about dimension 3? It's also contractible. There's two ways of proving that nowadays. Hatcher did, in some sense, a flow argument, very complicated. But there's now actually a Ritchie flow argument as well that proves this in dimension 3. So at this point, you might be worried that this talk is about spaces that are all contractible. But that's not true in high dimensions, where algebraic topology kicks in. Okay, so it's definitely not contractible. In fact, also not in dimension 4. And I'm going to give some examples of this, and you'll see many path components appearing then. So here's a way of constructing an invariant of a path component of the group of diffeomorphisms of a d-dimensional disk. Okay, so what do? Let me draw the disk like this. This disk sits inside of a sphere. So I can take my diffeomorphism over here and extend it by the identity to the rest of the sphere. And then I can use that to glue two half disks together. Extend the diffeomorphism to the sphere, glue two half disks together, and what you get is something that is difficult to understand, but at least has the same homotopy type as a sphere. And what you get is a map from the set of path components of the diffeomorphisms of a d-dimensional disk to a group of oriented homotopy spheres up to orientation preserving diffeomorphism and the connected sum. So these are manifolds that are homotopy equivalent to a sphere and are of dimension d+1, but they might not be diffeomorphic to it. Now, of course, the question then is, do these even exist? how many are there? Can you actually hit any of them by this construction? And it turns out that, well, you can hit every one of them by this construction. And in fact, you can recover the diffeomorphism that you started with when you did your gluing construction from the original manifold. Oh, it's because all the map, so this only, the homotopy type of this guy only depends on the continuous map that you have over here. And by the Alexander trick for continuous maps, which is even easier than for homeomorphisms, there's nothing to check. Every one of these phi's is homotopic to the identity. So the space you get is homotopy equivalent to what you get when you just glue using the identity. Okay, so firstly, there is a bijection. And secondly, these groups are often non-trivial. So here's a table of the first couple of them. It was computed by Caver and Milner. This is how many elements there are in this group theta d+1, which is an abelian group. Okay, when I write it like this, it looks super mysterious. There is actually a reason behind all of these numbers, but at least you can see now that there's many path components in general. So you take connected sum. You connect some two spheres together, you again get something homotopy equivalent to a sphere. Yeah. And orientations are used to make this well defined. In fact, the inverse of every element is the same sphere but with the opposite orientation. Yeah. Okay, so for example, the first time that there's many path components, as far as we know, dimension 4 could be the exception to that, is when the dimension of your disk is 7. Sorry, I think there's a typo here. There should be a 6. Everything is shifted by 1. Okay, anyway. Let me just write down an example of an exotic sphere. The easiest one that exists. It's a quotient of 2 Lie groups. So that's the easy example that I'm aware of. In fact, the only example you can write is a quotient of 2 Lie groups, apart from the standard sphere. Okay. So what's been done recently in like the last, I wouldn't say that. Quaternions for sure, by definition, but I don't think quaternions are. Okay, so what's been more recent progress? So we focused on the following easier question, which is not what's the homotopy type of this group, not even what are the homotopy groups, but what are the homotopy groups if you tensor with Q? So these guys are abelian groups, all of them. It's definitely obvious when star is at least true, but it turns out to always be true because you can stack diffeomorphisms. So we wanted to know when you tensor with Q, just take the non-torsion, sorry, the non-torsion subgroup. How large is that? Of course, you must first think about, is this a reasonable question? And the answer is, it's almost always a reasonable question. So I proved in my thesis that these are in fact finite dimensional vector spaces. So there is an actual number. As long as the dimension is at least 6, but not equal to 7, but then with Manuel Carnage, I figured out a trick to also get the 7-dimensional case. 5 is still open. Actually, I don't know how to do for dimension 5. So anyway, this is a number you can now ask about for every star. Okay, so how do you even get information about this? This entire story about these disk bundles that I was explaining is used for that. So all the invariants that we have do the following thing. They use this bijection between homotopy groups of the diffeomorphism group and disk bundles, and then construct invariants of disk bundles. And then hopefully show that many of those are non-zero, and that means that there must be some elements in these homotopy groups. Characteristic class just means that these invariants behave in a particularly nice way under pullback of disk bundles. Okay, so there's 3 known sources. The first one is called higher Whitehead torsion. The second one is called configuration space integrals, and the last one are Pontryagin Weiss classes. I'll explain all of these because they all relate to a different aspect of mathematics that is not differential topology. Okay, so the first one is these higher Whitehead torsions, which are related to algebra and number theory. Okay, so they're only non-zero in odd dimensions. They're given by certain characteristic classes called higher Whitehead torsion classes that were invented by Iguza. And Hatcher and Waldhausen constructed by hand a bunch of odd-dimensional disk bundles, and then Iguza proved that the composition is not zero, which means that there must be some non-zero homotopy groups in the diffeomorphism of odd-dimensional disks. So what are these characteristic classes doing? They want to take the chain complexes for computing homology of each of the fibers. Because these are the chain complexes computing the homology of a disk, they must like basically have trivial homology, only homology in the bottom degree, because these guys are homotopy equivalent to just a point. The question now is, can you make them have no homology by only doing certain types of moves called elementary operations? You can always do this if you have a single one of these chain complexes. That's some basic algebra effect, but in families it might be difficult to do. And it turns out that whether it's possible to do that is measured by algebraic K-theory of the integers. So using these types of invariants in a slightly different form given by Waldhausen, people are able to perform the following computation. So it says that if you have a d-dimensional disk in a quite small range of degrees, namely at most a third the dimension, the homotopy groups are either zero, rationally, if d is even, or they're given by the algebraic K-theory of the integers. And those were computed by Borel, using, I guess, studying the geometry of certain symmetric spaces and defining certain special differential forms on that. It's a very interesting story that goes very much in like a number theoretic direction.
So where is it bound?
The bound comes from Iguza's pseudo-isotopy stability theorem. Maybe you know this fact that if you have a Morse function on a manifold that looks like a lower dimensional manifold times an interval, and that manifold happens to be, no, let me say it slightly differently. There's some tricks you can do where you cancel critical points in Morse functions to concentrate them only in a few degrees. It's called Handel trading. And then there's usually in general some kind of algebraic K-theory obstruction to completely getting rid of all the critical points. You could try to do this in families for Morse functions. And it turns out that then there's some general position arguments you have to do. And those general position arguments will work up to some point in families, but not always. And that's where that bound comes from. This is some kind of Morse theory in families that shows up secretly in Iguza stability. Yeah, but anyway, okay, so we get nothing interesting in even dimensions, and we get a Q every 4 degrees in odd dimensions from this. Okay, so that's the first source, these higher Whitehead torsions. The second source are configuration space integrals, which were inspired by mathematical physics. Okay, so these were originally defined by Kontsevich. They're invariants of d-dimensional disk bundles. And then Watanabe discovered how to generalize a construction in dimension 3 called Clasper constructions for knots to give interesting bundles of disks. And then also proved that the composition is not zero. So if you evaluate Kontsevich's configuration space integral classes on these Clasper bundles, you get something non-trivial. And what are these characteristic classes? How do they detect that the bundle is non-trivial? Basically, what they do is they look at the configuration spaces of points in each of the fibers. You can do this for each number of points you might be interested in. You get a bunch of configuration space bundles. There's maps relating these to each other that forget points or double points. And then it uses certain differential forms that were inspired by perturbative quantum field theory to extract numbers from these objects. So in some sense, it's measuring to what extent these configuration space bundles can't coherently be trivialized. Okay, and so Watanabe used this to prove the following theorem, that the homology of a certain combinatorially defined chain complex of graphs, called a graph complex, this injects into the homotopy groups of the diffeomorphisms of a disk. These things are very difficult, even though they have an easy definition. So computer calculations give the dimensions of these groups. But let me just show you some examples. So it's a complex of, okay, sometimes I've added a superscript 2. The superscript 2 is a simplification of the one without the superscript that has the same homology. And it means that you're not gonna allow univalent or bivalent vertices. So it just makes it a little bit easier. So you get at least trivalent graphs, orientations depending on the parity. You take formal linear combinations of those, and then you put them in a particular degree depending on how many edges and vertices you have. And there's a differential on this chain complex that sums over all ways of contracting an edge, and then you have to keep track of some orientations. Okay, so there's some numbers, many of them are 1, they actually go super exponentially. But what are some of these ones? Well, one of them is generated by a tetrahedron. That's still understandable. The next non-trivial one is already this crazy combination of graphs. And it becomes almost impossible for humans to understand the structure that's going on in these guys. But there are many, many interesting classes. Okay, and finally, these are maybe the most subtle ones. You can use the topological manifolds theory and the link to homeomorphisms of the Euclidean space to actually produce certain characteristic classes of disk bundles. Okay, so these were, I guess, invented by Michael Weiss, and this interpretation of, or the construction of these particular bundles is due to myself and Manuel Carnage that detect them. So what do you do? So this Alexander trick that I mentioned said that homeomorphisms of the D-disk are contractible. And that has an interpretation in terms of bundles as well. It says that if you take a smooth disk bundle, but forget the smooth structure, you can make it trivial. You can just make it a product. Okay? And you can use this fact to get certain secondary characteristic classes of smooth disk bundles, as long as you have a class in the cohomology of the classifying space of this group of homeomorphisms of the Euclidean space that goes to 0 when you restrict it to a cohomology class in the cohomology of the classifying space of the orthogonal group. We know really well the cohomology of the orthogonal group. It's given by Pontryagin classes. That's a classical computation by Milner-Stashev. The cohomology of the classifying space of top D is much more mysterious. But luckily, Michael Weiss and Galatius and Mendel Williams figured out that there's many, many examples. So what is the computation of the cohomology of BOD? It's given by an algebra in Pontryagin classes, PI, free-graded commutative algebra, when for I at most D. And what this theorem says is that you can also define PIs for I bigger than D. In the smooth case, on BOD, those are 0, but on B top D, they're not 0. And so these guys can be Cs that serve as input for these secondary classes. And then we used those to prove that you can inject a very large collection of homotopy groups into the homotopy group of diffeomorphisms of a disk. So let me put that theorem up there and say what the domain is. So by Kirby-Siebenmann, the domain of this injection is Q every 4 degrees and 0 otherwise.
In the first theorem, was that I, is for I greater than equal to B?
Oh, there should be a star. Yeah, it should be a star. Oh, that shouldn't be no, that shouldn't be anything. This is just true. Sorry, no, star should be bigger than D. Yes, you're right. Sorry, I made that. Yeah.
The first endurance you had, it was like star less than D over 3, and now you're, I mean, like.
Yeah. Yeah, this is all about things that are far outside of the range where this computation of Farrell Hishang from the 70s worked. Yeah, so that gives us the following conclusion. We have these 3 contributions, the only known contributions to the rational homotopy groups of this group of diffeomorphisms of a disk. The algebraic K-theory of D integers, but only when D is odd, some graph homology, and these Pontryagin-Weiss classes. And the complete computation, as you mentioned, is only possible in a very small range of degrees, and basically all of these guys live outside of that range, except the algebraic K-theory of the integers. And so the question is, are there more elements than these? And the answer is, well, we don't completely know, but in the even dimensional case, in large regions, we can exclude any other classes. This is impossible to parse, so this is what you should actually be looking at. So I've only drawn the even dimensional case here. The dimension is on the x-axis, going from 6 up to 40, and star is the degree of the homotopy group. So this is a picture of the rational homotopy of the diffeomorphisms of the 2n disk. So I have these solid dots. These are these Pontryagin Rice classes that I mentioned, a Q every 4 degrees that inject into the rational homotopy. These boxes, the red boxes with a dot in the middle, those are these graph homology classes that Watanabe proved inject in the homotopy of the diffeomorphism of a disk. There's no K-theory because we're in even dimension here. When I haven't drawn a solid band of color, there's like a bunch of them visible near the top left. Whenever I haven't drawn those, the answer is 0, unless there's a dot or a square. So there's nothing else. What are these color bands? That's bands where we don't completely understand what happens. The graph homology is in there. We think that's the only thing that's in there. It's completely compatible with our computations, that's the case. But we don't know exactly that everything cancels out in the way it's supposed to just give you graph homology. Yeah. So there's something, when you have a disk, you can reflect it. This reflection diffeomorphism is not in the group. So conjugating with it gives an outer automorphism, and that acts non-trivially on these homotopy groups. The colors indicate what the action of this involution is. So I think if I remember correctly, the blue one is +1, the orange one is -1, and what's supposed to be gray is where we have both plus and minuses contributing. Yeah, so it's just something that helps you keep track of some extra data, which philosophically actually for a bunch of proofs is a very important thing. If you have extra symmetries around, you should let them act because the representation theory helps you distinguish many things from each other. What is this weird dotted line at the bottom? That's this d/3 range. So before our work, we only knew that in the even dimensional case, you had nothing below that line, but now we know that this is the picture. And so the conjecture is that actually those bands are all just contain only these boxes, and that you can make this picture complete by just erasing them. Okay, so that's what I said over here. We're trying to prove that these are the only contributions, the boxes and the dots, and that those bands of uncertainty are actually just empty. In odd dimensions, there's less strong work. So Kranich and Randall Williams proved that in the range 3/2 of D, which is still much better than 1/3 of D. In odd dimensions, you only have the 3 contributions that I mentioned, and conjecturally, these are the only ones as well in all degrees, but that's not as plausible an approach for doing that. Okay, so maybe I'll spend the last 10 minutes explaining a little bit about why can we do these computations now? Why couldn't people do them 10 years ago? And it's because we have 2 new techniques available. The first one involves stabilizing our manifold and then use results from homological stability and cobordism categories in this more stable world, and then destabilize back again using something called embedding calculus. So I'll explain that now. So you start with the disk. Let's say of even dimension, and you add a bunch of Sn times Sn's. So maybe it looks like this when G is 3 and N is 1. These are the higher dimensional analogs of genus G surfaces with 1 boundary component. So that's how we stabilize. We study these manifolds, and in fact, we're going to want to let G go to infinity. But then the problem is, like, how does that relate at all to the original disk we were interested in? And that's where this destabilization techniques comes in. We want to compare the diffeomorphisms of this manifold to a certain space of self-embeddings, namely those that fix only half the boundary but map the rest of the boundary into the manifold, so that the complement, as this picture indicates, is a disk. That will automatically be true by the H-cobordism theorem. Okay. So that's the space of embeddings that I mentioned, the space of self-embeddings of this manifold into itself that fix half of the boundary pointwise. And then this wise fiber sequence that I brought up at some point says that actually the difference between the diffeomorphisms and the self-embeddings is exactly the diffeomorphisms of a disk. Okay, fiber sequence is a term from homotopy theory, but the way you should read this is that the term that's on the left is the difference of the middle and the right term. Okay, so at some point I mentioned you could measure the difference between inserting a disk in your manifold and taking the diffeomorphisms of a disk or the diffeomorphism of the entire manifold, and this is a way of making that precise. It's given by some space of self-embeddings.
Would it be helpful to pass this through?
Yeah, that doesn't seem obvious that it's helpful at all. Okay, there's a general case. So how do you use this? So you first want to compute the rational homotopy in the middle term. And it turns out that you can do this, it's not easy, as g goes to infinity. I think this is a bit of a counterintuitive philosophy in mathematics, but it turns out that many groups that you might study that are automorphisms of some kind of object. Maybe it's a manifold, maybe it's just z to the n, and you look at g, l, n, z. Many of these groups become easy to understand as the parameter goes to infinity. The idea being that you have more space to do certain constructions in your group. In here, that's certainly true. So the work on stable moduli spaces of manifolds by Glaciers and Render-Williams helps you, but doesn't immediately give you, there's still a lot of work to do, a way to compute something about the rational homotopy groups of the middle term. You can also get at the rational homotopy groups of the right term. That does not depend on letting g go to infinity. It becomes certainly easier for a reason I'll explain, but it's actually possible in general, using something called embedding calculus. Okay, and then you just compare the two. Where does the band of uncertainty come from? It's how exactly the two terms map to each other. Might not be so easy to figure out what happens there. Okay. So this helps us understand the graph I gave before a little bit better. So in this picture, the dots, which are these Pontryagin and Weiss classes, and just the very top line of each of these colored bands, those come from the middle term of the diffeomorphisms of a disk. The rest of the bands and also the squares come from the self-embeddings. I guess I should have added that. Yeah, okay. Understanding how these exactly relate to each other helps us understand, hopefully in the future, that these bands don't actually contribute anything to the disks. Okay, so let me talk a little bit about this first step, computing the rational homotopy of the diffeomorphisms, because that's 4 papers by itself to do that. So what does this work of Glaciers and Render-Williams do? It tells us just how to compute the homology of this space rationally in a range that goes to infinity as g goes to infinity. But what we wanted were the rational homotopy groups. If your space is simply connected, it's not so difficult to go between them. But this space is very much not simply connected. Why is that? Well, in general, I mentioned that pi1 of a classifying space is pi0 of the group that you have. So here it's isotopy class of diffeomorphisms of this n log of a surface. Maybe you've seen mapping class groups of surfaces. You know, those are very, very complicated, have infinitely many elements in them. The same is true here. And they act in a very complicated way on the higher homotopy groups. Let me just tell you what happens in high dimensions. Okay, the situation is a bit better than in the case of surfaces. If you act on homology, the homology of your manifold, what is that? That's z to the 2g with a particular form on it, given by the intersection form of n-dimensional cycles in a 2n-dimensional manifold. And that's either a symplectic group over the integers or an orthogonal group over the integers, depending on what the dimension is. And basically, this is surjective. You hit a finite index. And so there is a kernel, but the kernel is actually a abelian group. So that's not so bad to deal with. This is true when n is at least 3. So in dimension at least 6. Oh, I mean, actually, this statement, I guess, is true in all dimensions. The fact that the kernel is easy to understand is only true in high dimensions. Okay, so what we're going to do is just take the elements that act trivially on homology, act as identity on homology, which is called a Torelli group. It's easy to understand because it has less path components, but still has the same higher homotopy group. We just restricted our attention to a few path components. And so what we proved using this calculus of embeddings that I haven't mentioned yet is that when you take the classifying space of this group, you get a space that is nice. The technical term is nilpotent, which means you can relate the homology to the homotopy groups. Moreover, when you take the rational homotopy groups, they will have an action of this group G on it, which is this arithmetic group. And actually, the representations that you get are so-called algebraic representations. They extend from the group defined over the integers to the group defined over the rationals. And then the coefficients of your representation are just polynomials in the entries. Those are classified, so you can actually try and name them, which is very convenient. And so through this fact, we can now go back to the work of Glacius and Randall-Williams on the homology of diffeomorphism groups and insert not Q coefficients, but coefficients that are representations of these algebraic representations of this group. And it turns out that with some trickery, their machinery also allows you to compute those groups. And once you understand that, it's a matter of somewhat hard bookkeeping in representation theory to then deduce what the homotopy groups are. So secretly, there's quite a lot of representation theory of algebraic groups going into this discussion. Okay, so that's my summary of one part of the. So maybe I'll stop here.
All right, thank you very much for this wonderful talk. Maybe there are any questions.
Let me just go back to the chart since that's the easiest thing to ask questions about.
Lukashin, maybe use this.
People love the chart.
Okay, so about this chart, it seems there is big discrepancy between this D over 3 and where actual elements are. So you have some conjecture about this, or I didn't understand. Maybe you said it, but
oh no, I mean we just improve the D over 3 bound to this is like twice a dimension.
Ah, I see.
That's where we know everything, and there's some uncertainty.
Right. And what is this lower bound? Is which line? Yes.
Like 2.
Ah, it's like 2n, 2D. Okay, 4n. I see. Okay.
Yeah, in that below that line, you only have these. The all dimensional case, the line is 3n. I guess when the dimension is 2n plus 1. And then also have the algebraic case every 4 degrees that you don't see here. I mean, secretly they're also here, but the thing that actually appears is those classes, the invariance of those classes on the dimension. And it turns out that the invariants are everything in all dimensions, and the invariants are 0 in even dimensions. So secretly they're also here, but they just happen to not. The right answer is not 0 in that case.
Right. Okay. Thank you. Yeah, I didn't understand I thought it is unknown what is in between the two lines.
No.
Is not, okay, yeah. Okay, great. Thank you.
There's nothing there.
Maybe some other questions. So I have a question. So these homotopy groups in principle have also a sort of Lie algebra structure. So does it show up, or do you know anything about it?
Sure.
It's trivial? Ah,
It's
okay.
because of the special structure of this particular space, which is has a stacking operation. And that makes then H space, and that makes the wide bracket vanish.
Oh yeah, it's an H space. I see.
But it's a very reasonable question for manifolds that are not a disk, like these stabilized guys. And in that case, you can say things about it. A small variant of this, where you Okay. The reason that only the top edge of one of these bands comes from diffeomorphisms, and there's not somehow a larger contribution, it has to do with the fact that the small variation of the homotopy Lie algebra for the diffeomorphisms of the manifold is equivalent to the algebra, which is actually quite nice. But yeah, which we also proved. We proved it. One reason is to cut down a lot of the uncertainty. Originally, these bands were twice as big.
From my older times,
Yeah.
in the rational homotopy,
Yeah.
Sometimes the growth of these groups in for higher higher dimensions is controlled by how the algebra grows. But,
Yeah. But this one is
yeah.
this one's not interesting as Lie algebra. Yeah.
I don't know if there are any other questions people online. That's a moment to ask. No question online. So then I have a very, before we give another, I have a special little present to give, which is a medal. So the prize comes with a medal, and so I'm going to take the medal. And so congratulations again. So that's it. Next one. No.
Why the embeddings are good idea. This is quite long, but I can tell you it's like a hint of why this might be a good idea. Yeah. Which is that
Thank you.